Hello guys, and welcome back to Introduction to Number Theory. Now we will discuss decomposition into prime factors in the ring of complex integers. First, let me remind you of what this ring is. Well, we say that z is a complex integer if it's just a complex number with integer real and imaginary part. Well, here I is, of course, the imaginary unit. For this ring, we define the norm in the following way. And the norm defined this way has a very convenient property which could be very useful for decomposing complex integers into prime factors. Namely, for any two complex integers, we have that the norm of their product is equal to the product of norms of each of these elements separately. From this, just notice, it follows that if a complex integer has a prime norm, prime meaning as just an integer. So if this is prime, if norm of z is prime, just in set of all integers, then z itself is prime when considered as a complex integer. So now let us see how we can decompose complex integers on a certain example. And for this purpose, I would like to consider complex integer number equal to 8 minus I, where I is the imaginary unit. Well, n doesn't seem so decomposable, right? We clearly cannot notice that it can be represented as a sum product of some different complex integers. But this means that we need to use our previous property of the norm and just calculate the norm of n. Well, norm of n, as we know, is equal to 8 squared plus 1 squared. This is equal to 65. We understand that 65 is a compound number, it's not prime. So we compose 65 into product. I can do it right here. So 65 is 5 multiplied by 13. So 5 and 13 are prime. But this means that we should look for a decomposition of n into factors, norms of which are equal to 5 and 13. So let's suppose that norm of A is equal to 5 and norm of B is equal to 13. Am I saying now that n can be decomposed into such elements, into product of such elements? Well, actually, no. All I'm saying is that if we want to find the decomposition of n, then these elements must have norms equal to 5 and 13 correspondingly. Now we need to try to find these A and B, which is much simpler now that we know their norms. Well, we will not be trying to find them simultaneously. We'll try to find one of them, and the second will be just equal to n divided by the first one. So if we take a look at their norms, well, norm 5 is much less than norm 13. So why don't we start from A and try to find the divisor of n with norm equal to 5. For that purpose, we'd like to take a look at all complex integer numbers with norm equal to 5. Let's draw complex plane. Well, not all of it, but just part of it. And we understand that if norm of A is equal to 5, and 5 is equal to 2 square plus 1 square, then imaginary part and real part of A, one of them is equal to 2 or minus 2, and the other one is equal to 1 or minus 1. We understand that there are actually 8 such complex numbers. Let's just draw them all on this plane. Say that this is 2, this is also 2, this is a real part line, this is the imaginary part line, and this is, over here we have minus 2, and over here we have also minus 2, but imaginary minus 2, and also 1, minus 1, 1, and minus 1. And now let's find these complex integer numbers with norm equal to 5. So we have indeed 8 such complex integers. I believe it's clear that all these points have real part equal to 2 or minus 2 or 1 or minus 1, and same about the imaginary part, so I don't need to connect these points with lines. Do we need to check whether n is actually divisible by all these 8 numbers? Well, this seems to be a very large amount of work. Can we somehow shorten it? Yes, of course. We can notice that not all of these numbers are actually different from the point of view of division. Actually, these 4 numbers, these 4 complex integers, and this, well, if we denote this one by A1, then this one here is equal to A1 multiplied by I, which means that if any complex integer is divisible by A1, that it is also at the same time divisible by A1 multiplied by I. These 2 elements are associated. And also this one element here is minus A1, and this one here is, we'll say, minus A1 multiplied by I. I is still the imaginary unit, and can also be represented in the form A1 multiplied by minus I. So of all these 4 yellow elements, we need to check for just one of them whether n is divisible by this element. Because if we find that it is not divisible, that it is certainly not divisible by all other yellow elements. Also, we have 4 other points. This one here, denoted A2, and this one, and this one, and this one. And we understand that this one is equal to A2 times I, and this way is associated with A2, and also this one is associated with A2, and also this one here. So all we need to check now is whether n is divisible or not by one of these 2 elements, which will automatically mean that n is either divisible or not by any other of these elements. So now let's take A1. It is equal to 1 plus 2i. This would be our first case, and our second case will be a2, which is equal to 2 plus I. And just try to divide n into a1 and then into a2 and see whether we get complex integer or not. First case, a1. Well, n is equal to 8 minus I, and we simply divide it as a complex number by 1 plus 2i, and we use the standard algorithm for dividing two complex numbers. We multiply both the numerator and denominator by the conjugate of the denominator, 1 minus 2i, and here we have, since it is a product of two conjugated numbers, then we have 1 square plus 2 square. So now it is equal to, well, 8, and imaginary unit multiplied by two imaginary units is actually minus 2. So 8 minus 2 gives us 6, and minus imaginary unit multiplied by minus 16 imaginary units gives us, I believe, minus 17 imaginary units. Let me check this one. Minus 1 and minus 16. Well, it seems so. Minus 17 imaginary units over 5. Over 5. So we understand that when we calculate here the real part and the imaginary part, this element, if we can call it this way, this complex number will not have integer real and imaginary parts. So 8 minus I is not divisible by 1 plus 2i. Let us now check the second case. So in the first case, we did not find any divisors. Second case, 8 minus 1, we should divide by 2 plus I. And we use the same, of course, standard algorithm for dividing one complex number into another. And here in the denominator, we once again get 5, 2 square plus 1 square. And now let's just calculate the denominator of this fraction. Well, once again, here we go. 8 times 2 is 16. Imaginary unit multiplied by imaginary unit is equal to minus 1. So 16 minus 1 gives us 15, which gives us some hope because 15 is divisible by 5. And what about the imaginary part? Well, minus 2 imaginary units multiplied by minus 8 imaginary units. So minus 2 and minus 8 gives us minus 10 imaginary units. And we see that this number actually is complex integer equal to 3 minus 2i. So now we can write that our n, which was equal to 8 minus I, is equal to the product of 2 plus I, the first divisor, and over here we gained 3 minus 2i. Now let's just notice that both these complex integers are prime when considered as complex integers, because the norm of this one is equal to 5, which is prime, and the norm of this one is equal to 13, which is also prime. So this way, we obtained the desired decomposition of n into prime factors, and this method can be used when given even more complex complex integers than 8 minus I. It simply works for any case at all.